Problem 9. Derive a formula for the volume of a right circular cone of radius r and height h. So, we have a cone, and it has, for its base, it has a circle of radius r, from there to there, and it has some height h. And height, of course, is measured this way, right? And some h. Now, what we want is a formula for the volume. In other words, we want a function of two variables, r and h, so that you give me any actual radius, say 5, and any actual height, say 3, we could plug those into here and find what the actual volume is. Now, when we did the review, I made this very suggestive. I said you're going to have something like this. And there are really two ways you can orient this to find a volume. And so, one way of doing that would be to think of this cone dead on like this, right? And think about it as a cross section here. And we can orient this on the XY axes, like this and like this. Of course, you could do this a bunch of different ways. You could put this cone over here and figure it out that way. You could put it up here and figure it out that way. But doing it this way would be pretty easy. Then the only thing is, well, we're trying to find a volume. This is a volume of revolution, right? And so we're going to take this thing and rotate it around like this. Take little slices of it and rotate it around, right? And you could do this, and then all we need to know then is at any given x here, what is this height y? And if we set it up this way, then this y is an mx plus b, right? It's a line, mx plus b, like that. The b in this case would be the height, which happens to be the radius, right? So the r, that would be easy. We could get mx plus r. Now we just need to find the slope, which would be, since this length from here to here is h, right? Then the slope would be the rise over the run, but it's a fall, so it's got to be negative. So it falls by r, negative r over h, right? So the rise is a fall of goes down by negative r every time it runs a total of h. So you would have negative r over hx plus r. And that would be the formula for this function. However, I'm going to go ahead and put this right over here. This is one way you could have done it. Minus r over hx plus r. A better way of doing it, though, what I think would be easier, would be to orient this thing this way, where we put the tip here at the origin, and then we have the cone like this. Its height is h, so we're going out here to h on the x-axis. Its height here is still r, so we have this, and now we know we're about to do a volume of revolution. So really all we care about is if we could find what this height is here at x, we're going to take that, rotate it around, right, like that, and then add up all of these disks. We're going to find the volume of that disk and add up all the disks as x goes from 0 up to h. Now in this case, this function here, it's still a line, y equals mx plus b. Now the b obviously is 0, so that makes my life a lot easier. Y equals mx plus 0. Now we just need the slope, which is the rise over the run. It's the same because it's a constant, it's just a line, so the rise is r, the run is h, so we have r over h is the slope times x, and that's the function we want to integrate. And so again, right, we're doing a volume of revolution. So we're going to find the volume of the ith bit of it. Volume is an area times a depth or a length, and in this case that length is, we're going to say delta x because we're going to chop up the x-axis. And so that's AI times delta x. That area is the area of a circle. And the area of a circle is pi r squared. Pi r squared delta x will be the ith volume. R in this case, not this R, right? We're talking about the actual value right here. That's for this disk. It's this value here at x, and it has a height of, well, we found the formula of the line. That's r h times x. So that's the height right there, or the radius of this disk. So that's what I'm going to plug in here. I have r over hx squared. That's the ith volume. And so I want to get the full volume, which is what I get if I sum up all of the volumes, all of the VIs. And here we're going to go as I goes from 0 up to n. And so now I've chopped this thing up into n bits, right? I'm adding them all up, but I want the actual volume, so I'm going to take the limit as n, as n goes to infinity of that. So I'm going to chop it up infinitely much and get infinitely many volumes that I'm adding up. And that's the same thing as the integral. From where? Well, from 0 up to h. So from 0 up to h of the VIs, right? Which are these guys right here. So that's pi r over h, times x all squared. The delta x turns into dx in the limit, and that's what we need to figure out now. Now you can see why I didn't want to do this, because had we done this, we would have ended up with a 0 up to h of pi. Now that is the height that we're squaring. That's the radius of the disk right there. That radius is minus r over hx plus r, r, and then I square it dx. Still doable. It's not really that bad. You could do a u substitution to make it easy, or you could just square this out. But it is a bit more complicated than this. Either way you do it, you'll get the right answer, but this way is just more straightforward. So let's plug along with this. We're going to say then the volume that we want, which is dependent on both r and h, is going to be the integral from 0 up to h of pi r over h x all squared dx. So let's do that. First off, let's square this guy out. And we have from 0 up to h pi. This is the same as r squared over h squared x squared, then dx. Everything that's not an x, in this case, as far as this integral is concerned, is a constant. So I'm going to pull them out. And so we have a pi r squared over h squared. Those are all my constants. All I'm left with is an x squared dx going from 0 to h. So that's an antiderivative, r squared, h squared. The antiderivative of x squared is 1/3 x cubed, evaluated up at h and down at 0. So that's pi r squared h squared 1/3 h cubed minus 1/3 0 cubed. That makes that whole thing go into 0, so we're done there. And what we get now is this constant, pi r squared. We have our h squared in the bottom. I'm going to pull him out as a constant, keep him in the denominator, times h cubed. Now some stuff cancels, and that's nice. The h squared cancels with 2 of these guys, leaving me 1 of them, and I could rewrite this as pi r squared h all over 3. So that is the formula for the volume of this guy. And so the volume in terms of r and h as a function is pi r squared h all over 3. Problem 10. Derive a formula for the surface area of an empty right circular cone of radius r and height h. Empty here means that you may ignore the circular lid or base. Okay, so what I said this in the review, and I hope it's clear by what I said here. You have a cone. We want the surface area, but we want to ignore this part, the lid part, right? So you imagine if this thing is solid, an empty, or rather it's an empty cone. And what we're doing, we're going to take that top off, basically, right? And so we only care about the surface area of the outside. That's what we want to do. Okay, so let's recall, I'm not going to go through the whole derivation again, but let's recall how we do the surface area of a volume of revolution. You have some function f, and you want to rotate this thing around the x-axis like this, and now you have a volume, right? It does something like that. And in order to get the surface area of it, we chopped up the domain and we said, okay, if you're here at x, then the surface area is what, the surface area of this band of it is what you would get if you found the surface area of this band of a cone, right? And we went through and found that the surface area of a band of a cone is 2 pi r times this bit right there that we called the length, right? And that took forever to figure that out, that was the surface area. I'm going to use S for that, so that would be the ith surface area. And then when you add them all up to get the full surface area, right? You add them all up and you take a limit, then this thing ends up being the arc length from here to here, and what we end up with is an integral from, let's call this A and let's call this B on the domain. So you're integrating from A up to B of 2 pi, the R in this case was this guy right here, and that, if this is F, then that height is given by f of x. You plug in your x, that gives you the height, so you've got your f of x. And then the length part in the limit turned into the actual arc length, 1 plus f prime x squared dx. So that's what we're looking for. We want the surface area. I was like in the middle of drawing a big S and I was thinking an integral at the same time. So the surface area is given by the integral from A to B of 2 pi f, 1 plus, the square root of 1 plus f prime squared dx. That's what we're going to be working with. The only thing we need to figure out now is really what's f. And if you did the previous problem, problem 10, you know that we could do this rather easily by just orienting the cone, putting the tip of the cone here at the origin, and then saying, okay, if I had this line and I rotated it around, right, that would give me my cone, right, because it's in the last problem it was a volume of revolution. Here we're doing a surface of revolution. And so, okay, then this would be my f, which is a line, mx plus b. And like we said before, orienting it this way makes it easy. This is 0, this is h, the radius here is r, right? And so mx plus b, well, the b is 0, so we have mx plus 0. And then the m is the rise over the run, which is r over h. So this is just r over hx. Too easy. Now we are just going to plug this in, right? The only thing we need f of x, which is that guy, and we need f prime of x. Well, that's easy enough. F prime of x is just take the derivative of that, r over h. It's a constant. How nice. How nice that on your final, when you had to do this, I gave you a constant in here. So you're taking the square root of a constant. It's just going to be a constant. How nice is that? You're welcome. So, let's plug it in. We get the surface area. And notice, right, that's the surface area of this part. It does not include the lid or the base of the cone, right? And so, we don't have to then add on whatever that base would be, which would be, I guess, 2 pi, in this case, r, right? I mean, sorry, pi r squared, right? That would be if we cared about the lid. We don't care about the lid. We are just doing this, okay? So, okay, let's plug all that stuff in. A to B is 0 to h, going from 0 up to h. 2 pi, f of x is r over hx. 1 plus, so the square root of 1 plus f prime squared. F prime is just r over h, and then we square it dx. Let's make our lives a little bit easier here by pulling out the constants. So I'm going to start here. I'm going to pull out 2 pi r over h. That's all one constant. So that's 2 pi r over h. I have the integral of, now it's just x. Now this square root, I'm going to operate on him a little bit to make him look better too. That's the square root of 1 plus r squared over h squared. Multiply, actually let's just get a common denominator over here. I'm going to call 1 the same thing as h squared over h squared. So that gives me a common denominator. So that whole thing is the same thing as h squared plus r squared over h squared, which is the same thing as square root h squared plus r squared over root h squared, which is just root h squared plus r squared over h. I'm taking the positive square root. Obviously, it should be obvious, everything here is positive. It doesn't make sense to have a negative in this case, so I'm just going to say, yep, that's got to be positive. So that's this constant right there, dx. And now I'm just going to pull that out. So that gives me, let's see, 2 pi r over h. Pulling him out gives me root r squared plus h squared all over h. And then we have our integral from 0 to h of just plain old x dx. Too easy. Okay, so in the next step, I'm going to simplify my constant a little bit. 2 pi r, the root stuff, root r squared, h squared, all over, that's h times h, that's h squared. Now, the antiderivative of this part. So that right there is just this right here. This, I can take the antiderivative of x, and I get 1/2 x squared. I'm going to evaluate him up at h and down at 0. So that gives me, let's see, 2 pi r root stuff. Actually, let me keep that down here. I'm running out of room. So, the constant is still 2 pi r root r squared plus h squared all over h squared. Now, we have, that's 1/2, plugging into h gives me h squared, minus 1/2, plugging into 0 gives me a 0, so he's gone. And so I just have that right there. Now, a few cancellations happen. Actually, 2 really nice cancellations happen. The 2 cancels the 2. And the h, which is in the numerator, h squared, cancels the h squared in the denominator. All I'm left with is pi r squared plus h squared. Should be the surface area of my cone. That's the surface area. And yes, it is a function of 2 variables, an r and an h. You give me any r, you give me any h, I can plug them into here, and I can find the surface area of that empty cone. Problem 11. Use your answers from problems 9 and 10 to answer the following. Holy cow! Ice cream and ice cream accessories, rights reserved, copyright limited, manufactures ice cream cones in the shape of empty right circular cones. Given that an ice cream cone must have a volume of 200 cubic centimeters, what cone dimensions minimize the cost of producing a cone? Assume that the cost is directly proportional to the amount of material used to make the cone. Give an exact answer, then plug it into a calculator and report an approximate answer. Okay, I did not explicitly state that the cost is proportional to the surface area, but that's what it is, right? If you're making a cone, you should be able to infer all of this, right? You're manufacturing an ice cream cone. The material that you use to do that is the actual material of the cone. We'll say it's a waffle cone. Look, yeah, it looks like that, okay? So there's your cone, looks like that. The material that you use is proportional to the surface area. Now, and so I said the cost is proportional to the material, which is proportional to the surface area. And what you could do if you wanted to make your life really hard is say, okay, so I need a cost. And that's proportional to the surface area, so K times, or rather, that's proportional to the material that I'm making. So there's some constant times however much material that is. But then you could say, well, that's proportional to, I don't know, some other kind of constant, how about KL times the surface area, and then you have your cost function, which is some constant times the surface function. But if it's just some constant, it won't matter. If this is your function C, whatever it happens to be, it looks like this. There's some kind of cost, or I guess I'm implying that you're minimizing it, so you're looking for a minimum. There's some kind of minimum for C. Well then, S is just that times some constant, so maybe, I don't know, maybe it comes up, or maybe it goes down, maybe it gets stretched down, or whatever. At any rate, it doesn't matter. That minimum is going to occur at the same point here, right? So if you find the minimum input value, then for any one of these, then you found the minimum input value for all of them. So all of that's to say that I don't need to see any of this, right? It's just, you should be able to infer that if you minimize the surface area, then you also minimize the cost, okay? So let's do that. How do we minimize the surface area? Well, surface area is a function of two variables. We don't know how to minimize a function of two variables. So what we're going to have to do is find some kind of constraint. And luckily one is given. We say that the volume has to be 200 centimeters cubed. So in other words, the output of this function has to be 200. So pi r squared h over 3 has to be 200. So what we're going to do is use this to get one variable in terms of the other variable. Now I think it'll be a lot easier if we get h all by itself. So I'm going to multiply the top by 3. Then I'm going to divide the pi r squared over here to get that h should be equal to, how about 600, make it a little bit nicer, 600 pi r squared. Now, I'm going to take that, substitute that in here for h, to get that my surface area now as just only a function of r is equal to pi r, the square root of r squared, and now instead of h squared I have 600 over pi r squared. So 600 over pi r squared, all squared, is now my surface area. So whatever this thing looks like, this is a function of one variable. I have S outputs for any R inputs. Maybe it does something like this. I don't know, but we're looking for this minimum value right here. And wherever that minimum value occurs, the slope is going to be 0 at that minimum value. And so I'm going to take a derivative and set it equal to 0, right? So there's my function. Let's take a derivative of it and set it equal to 0. Thing is, it's a function of r, and I notice that I have an r on the outside of a root. And if I want to just take a derivative of this thing, I'd have to use a product rule, right? I would say, okay, this is r times something, so the derivative of the r, it will have a pi times, okay, derivative of the r, leave the second thing alone, plus leave the r alone, take the derivative of this, and da-da-da-da-da. And like I said in the review, that's going to get really ugly really quick. So I said if you end up with something like this and you're about to take a derivative, go ahead and put that variable into here. So that's what I'm going to do. I'm going to rewrite this as pi root r squared times r squared plus 600. Now I'm going to go ahead and just rewrite this as 600 squared over pi squared. Now r to the 4th. Okay? But that r squared comes in. So now we just have a pi, and we have a r squared times the stuff that's in there. So we have a r squared plus 600 squared over pi squared r to the 4th. That's the same thing as pi. Distributing them over the addition, and we have r to the 4th. Hey, please keep it down. Please be quiet, thank you. Pi squared stays put. Now when the r squared jumps over, he kills 2 of the r's that are in the denominator, but not all of them, leaving 2 in the denominator, just like that. Okay, so that's how I'm going to write surface area. I'm going to get rid of this to give myself some room. Okay, actually, it'd probably be a good idea to keep him somewhere. H is equal to 600 over pi r squared. Because I asked, what dimensions do this? And I'm thinking, I'm about to do some calculus on this, find an r value. So I'll know the radius, that'll be one of the dimensions, but I'll also need the h. So I don't want to lose this. When I find r, I could plug it in here and find what h needs to be. Okay? So, okay, let's do this. We're going to rewrite the surface area over here. So the surface area as a function of r is equal to pi and then square root of this stuff. R to the 4th plus 600 squared pi squared r squared. Okay, so that's my surface area. Now it's been dropped down into one variable thanks to our constraint. And it should be much easier to take the derivative of this guy. So if we have an s of r equals something, root something, and I take the derivative of it, root something comes into the denominator. A 2 also drops into the denominator. And then we take the derivative of what the inside stuff is, right? So, okay, s prime of r, pi comes along for the ride. We get a 2 down here. Denominator stuff comes along for the ride, r to the 4th plus 600 pi squared r squared. Now we multiply by the derivative of all of this stuff. So we want the derivative of r squared. How about 600 over pi squared r to the negative 2 is a better way of writing that if we're about to take a derivative. So I'm going to take the derivative of all of that inside stuff and let's see what happens. 4 drops down and we get r cubed. And the next one, the negative 2 drops down, so negative 2 times 600 over pi squared. And then we subtract 1 off of there and we get r to the minus 3. I'm going to rewrite that as 4r cubed minus, why not, 1200 pi squared, and that I'm going to rewrite as r cubed in the denominator. Okay, so all of that right there is what goes up here, just like that. I take the derivative of the top stuff, or the inside stuff, and put it on the top, right? So, that's 4r cubed minus 1200 over pi squared cubed like that. Okay, so now we found our derivative. In other words, we had some function s, and we found where its slope is, well, we found the formula for its slope. Now what we're going to do is say that the minimum occurs wherever that slope is equal to 0. And what we're going to do is try to find the r value that makes that true. And so I just need to solve this right here. The great thing about this is it's equal to 0. I could just multiply both sides by whatever's in the denominator. Kill denominators, right? Going back to algebra 2 here. Kill denominators. Whenever you see them, try to kill them. So I'm going to go 2 times the root on that side, 2 times the root of the stuff on that side. That cancels that. We still just have a big fat 0 right there. That's nice. Pi 4r cubed minus 1200 pi squared r squared. Like that. Divide both sides by pi. He's going. Now we're just solving that. That's way easier to deal with. That's the same thing as this. Luckily there's a minus there. Nice how that works. Pi r cubed equals 1200 pi squared r cubed. It should have been a cubed there. I want to get all the r's on one side. That's easy enough. I'm going to multiply over here r cubed times r cubed, and I'm going to divide by the 4. So the 4 comes into the denominator like that. This is the same thing as r to the 6th. Now 1200 divided by 4 I think is 300. Right? Yeah, because 12 divided by 4 is 3. Yeah, so 300 all over pi squared is r to the 6th. And then, oh, look what I did. That should have been a 600 squared that whole time. That's why I thought, because I remember doing this and I didn't remember a 1200 coming along, right? So that should have been a 600 squared. So when did I get that? That was when I took the derivative of the inside stuff. That was r to the 4th plus 600 squared pi squared r to the negative 2. The derivative there should have been 4r cubed. The negative 2 comes down as that, and this is how I wrote it when I did it before, r to the negative 3. So the negative 3 comes down as r to the positive 3. And so now the only difference here is that this should have been 2 times 600 squared, like that. And so this should be 2 times 600 squared. Oh boy. Making this 2 times 600 squared. Now this is what I remember doing earlier. So this is 2 times 600 squared. And then, yes, that's what I got. I wrote this as 600 squared. The 2 cancels one of these and leaves me a 2 in the denominator. Pi squared. Now if you want, you could simplify that further. I mean, with the 600 and the 2, you could pull a 2 out of there and can't. But this just seems nice and easy to deal with right there. So I'm going to leave it there. Yours might look different, 600 times 600 over 2. You could write that as 200 times 600. 300 times 600, which would be what, 18 something? See, I don't know. This is fine. That's what that is. Now we need to get the r by itself. Take the 6th root of both sides to get r is equal to the 6th root of 600 squared over 2 pi squared. So that's one of the dimensions that minimizes this. So then the other one is going to be what I get when I plug this into here. Okay? So the exact answer is going to be h is 600 pi, now r squared. R is this. So that's 600 squared over 2 pi squared, or 1/6. And you can leave it like that. You could simplify this a little bit more by multiplying that 2, or, with the laws of exponentiation. You have this 2. That's the same thing as just multiplying this through like that. And so that would be that stuff to the 1/3. So if you like that, we could do that. And we could rewrite that as, this is 1/6. We could rewrite that as h equals 600 over pi, all of this to the 1/3, so that's 600 squared over 2 pi squared. However you want to do it, a lot of different ways of doing it. You could also bring some stuff up into the numerator, whatever. This is good. This is an exact answer. Plugging these values into Wolfram Alpha, I got that the radius should be 5.130529 centimeters, and that the height should be 7.255663 centimeters. Now, I'm not concerned with how many of these digits are significant here, because this isn't a chemistry class or a physics class. But knowing, well, I know, maybe you don't, that we're going to use these values later. We probably don't need to keep this many digits. In fact, I doubt that there's any manufacturer out there who could actually measure this far down to the millionth or whatever it is of a centimeter. Probably don't need to keep that, but I want to keep as many digits more digits than I think I need for doing subsequent calculations. This is a good rule of thumb always, no matter what you're doing. Keep more digits than you think you need, so that at the very end you could round it to what you want, but you don't want rounding error to creep in too early in your calculation. So I just chose to take 6. You could have taken less, but it's good form to keep the same number in both cases. Now, if you actually measure this out, if the radius is actually 5.13 centimeters, then that's what the top of your cone looks like. And if the height is actually 7.25 centimeters, that's what the height of your cone looks like. And you can see this does not look like a very ergonomically, very well designed cone. Like, you wouldn't want to hold that. You know what I mean? When you think of an ice cream cone, you probably think of it as being longer so that you could actually get your hand around it a little bit better, and you don't have, I mean, that's just awkward, right? So while this might minimize your cost in one sense, your cost function should probably have some more terms. Not only like, do you have this, that this is the price of your stuff, you know, the price of your stuff per surface area, price as a function of the surface area, so, and that's why we just minimized surface area. But you probably also have some term that has something to do with the design of it. Because if your cone looks like this, maybe your cone looks like that, but is anybody gonna buy that? No. So if nobody buys the cones that you make, your cost is essentially like near infinite, right? Or I mean, it's way too much. And so you would have another term in there that would constrain what you have. Like, maybe you have a minimal amount, like, we can't go past this. It can't be wider than this because people won't want to hold it and nobody's going to buy it. And so then you would have another term in here that would account for that. And then it would be a play between, when you go to minimize this function, it would be a play between how much surface area can we get away with not including, versus if you go too far, nobody's going to buy your cone if it looks like that, so don't go crazy. And so we're not actually solving any problems for Holy Cow ice cream and ice cream accessories here. So we're simplifying things by a lot. Info for problems 12 through 15. The Chief Financial Officer of Holy Cow Ice Cream and Ice Cream Accessories, Rights Reserved Copyright Limited, is trying to come up with a model for the company's profits for the next fiscal year. The problem is that if they manufacture too many cones, then the costs outweigh the benefits. Let X be the number of ice cream cones sold in 1 year. In general, a good model of profit is given by P of X equals R of X minus C of X, where P of X is the profit made by selling X cones, R of X is the revenue made by selling X cones, and C of X is how much it costs the company to make X cones. All of these functions take the number of cones produced as inputs and return dollars as outputs. Problem 12. If Holy Cow Ice Cream and Ice Cream Accessories, rights reserved, copyright limited, sells each cone for $1, write a function for R of X. Now remember, R of X is the revenue made by selling X cones. And I hope that this made sense, right? That your profit, the amount of money that your company makes, is the revenue, is just the total amount of money that you take in. This is money going into your company, minus the cost, which is the money spent to make the thing, or money out. So that the profit is the total amount of money that you end up with after you factor in how much it costs to produce the thing. That should make sense. And so, this is a total gimme right here, right? We want to know how much money do you make if you sell X cones. Well, if you sell for $1 a cone, let's just be really explicit here. You have X cones and you make $1. You sell them for $1 each. So in other words, you're making $1 per cone. If you multiply these two things together, then you get 1 times X dollars for every cone. Okay, so 1 times X dollars is what you've made. 1 times X dollars. So your revenue, the amount of money that you're taking in as a function of X, should just be X. If you sell X cones, you get X dollars. That was a gimme. I hope that didn't throw anybody through a loop. There's nothing tricky going on here. Should be a nice round X. Problem 13. The Chief Financial Officer gathers all data from the last 7 fiscal years to derive a formula for the cost function C of X. Plotting the data points with the number of cones produced, X, on the horizontal axis, and the cost, C, on the vertical, he notices the points do not fall on the line. Being well trained in applied mathematics, he immediately plots the change in cost with respect to cost. That is, dC dx versus C. And it's still nonlinear. He tries graphing dC dx versus x, and while it's nonlinear, he thinks he recognizes the curve. It almost looks like a logarithm. So being well trained in applied mathematics, he exponentiates all of his dC dx points and graphs them on the vertical axis along with the x points on the horizontal. Voila! All of the points appear to lie on a line with slope k that intersects the origin. That is, the data obeys the equation e to the dC dx equals k times x. Do whatever you need to do in order to turn this into a separable differential equation and find the general solution C of x. Okay, so what's going on here? There's a lot of things to say. So somebody's looking at some data and it looks like this, right? You have, this is the function you want. The input is x, the number of cones. The output is cost. And somebody's analyzing this and graphs it all and says that's not a straight line. I don't know what I could do with that. So one of the first things you try, like I said when we talked about this, is we just take the difference between each one of these. You find the slope from here to here. You find the slope from here to here. You find the slope from here to here. And those are now your output data points. And what you do now, your input data points are the costs themselves. So we take C1 and plot it right here. We take C2, plot it right here. And at C1, we compute the slope right here. And as you can see, at C1, the slope is negative, right? And then going from here to here, from C2 to C3, the slope is positive. So at C2, the slope is positive. And it's more positive from C3 to C4, so it goes up some. But now you do all this, and you see, still not a line. In fact, that looks even worse. I don't know what to do here. The last time we did this, we went from here to here, and everything got really nice. But now, not so much. So what do we do? Well, there's a lot of different things you could try. And this guy tried, well, why don't I keep these data points here, but now I'll graph the actual input values, the actual x values, the number of cones. And when he does that, he notices, hey, wait a minute, I almost recognize this curve. It's still a curve, so I can't just derive a differential equation from it because I'm not sure if that's a square root or a log or whatever it is. It might be something more exotic. But it looks like a log, and so maybe it is. If it is, then exponentiating all of these, this is just one of the things you would try. You would say, well, instead of plotting this point as C1, I'm going to take whatever that value is, and that's, you know, down here, it's like, let's just say it's that dc1 dx is like -3. So what I'm going to do is, what the point that I'm going to pair with that is just going to be e to that, e to the -3, some small positive number. And that's what I plot right there. Ditto with all of these, right? And you keep doing that, and you plot it, and you see, lo and behold, it's a straight line. Wow, great. And so he sees it's a straight line, and he computes the slope, right? And this is probably a succession of slopes, right? And then maybe take an average of all of those slopes, and he found that the slope, k, was whatever it is. I don't think I gave it to you in this problem. But given that that's the case now, we could say that this output, e to the dc dx, is equal to kx, because luckily, happily, this line happened to go through the origin. Isn't that nice? You're welcome. So this turned into something very simple that we could do. Okay, so that's what's going on with this problem, and this is indeed one of the things that you would try. Like I said before, you take this first step. This is almost always your first step if you're trying to fit this to something, and you would do this, but it's not always going to turn it into a nice line. So there are other things that you try. If that doesn't turn into a line, you might want to try something else. And this is one of the many things that you would do. You can also take the log of all of these points and plot them versus various things. You could do a lot of different things like this. This is indeed one of the things that you would do if you're trying to analyze some data. Okay, having said that, we are given a differential equation. It is an equation that involves a derivative of some unknown function c, and we want to find the general solution. We want to find that c. But again, general solution here means I'm looking for a family of functions. So, do whatever you need to do to solve this thing. Well, if it's like, man, if I just had this stuff by itself, then life would be a lot easier. Well, just get it by itself. Undo that by taking the log of both sides, right? If this is the thing that you want to get by itself, the way you undo that is you take the natural log of both sides here. What does that do? That makes this drop out. dc dx. The thing that we're looking for is now equal to log kx, where k is just some number. Okay? That is a separable differential equation. In fact, you could just integrate both sides like this, but if you want to think about it like this, we can separate it, get all of the x's on one side, all of the c's on another side, which is what we have, and then I'm just going to integrate both sides. Oh no. Alright, well this is gonna be some doing, but the antiderivative of dc is just c. So we have c plus some constant, c1, and then whatever this is. So let's work on that guy. That's the hard part here. Okay, so we have the integral of the natural log of some constant k times x dx. How about substitution by parts? I'm going to let you be this part right here, right? So that we have natural log of kx. I'm going to let dv be everything else, which is just dx. Why didn't I choose dv to be that stuff? Well, that's the integral we're trying to compute. If dv were the log stuff, I would have to find its antiderivative. That's not going to work. Ditto, if I let u be the dx, well then you take the derivative of it and it would be d squared x or dx squared. What is that? What does that mean? How does that help us? It doesn't. So this is easy. The antiderivative of dx is just x. And then the hard part here, the derivative of log of something is 1 over that something. Then you multiply by the derivative of the inside stuff. Kx is just k. So the k's are gone. Du is just 1 over x. So I'm going to rewrite it like that, 1 over x. Now, the integral of this is uv, so x log kx, minus the integral of v du. Okay, so the v is x, du is 1 over x dx. That's nice. X log kx minus the integral dx. The integral dx is just x, so x, natural log kx minus x. And then we'll have plus a constant. But let's just double check this and make sure that when I take the derivative of this thing, I do get back my integrand. So let's do that real quick. Kx minus x plus a constant, don't need to worry about it. Derivative of this. Product. So take the derivative of the first thing, leave the second thing alone. The derivative of x is 1. Add that 2. Leave the first thing alone, take the derivative of this thing. Well, we just did that. It worked out to be 1 over kx times k. So that's gone. Minus 1, because the derivative of that is 1. So we have log kx plus xk over x. Oh, look at that. That's nice. The k's cancel, the x's cancel. I have 1 minus 1 is just log kx. So that is indeed the antiderivative that we're looking for. And so this thing works out to be, this integral right here works out to be x log kx, whatever k happens to be, minus x plus c2. We're almost there. The cx is the thing I'm looking for. So I'm going to bring that c1 over here, and I get x log kx minus x plus c2 minus c1. But that itself is just some constant. So the general solution is x log kx minus x plus some constant c. There is the general solution. It's a family of functions that look like this, and they're shifted either up or down depending on what that constant c is. Problem 14. Given that the empirically derived slope that the chief financial officer found in problem 13 was k equals 0.0002091, and that the price of the cone material costs $0.001745 per square centimeter. Use your approximate answers from problem 11 and your result from problem 10 to find the cost of the cone, thereby giving us a particular solution corresponding to the cost of the optimally shaped cone you found earlier. Okay, reading that, I realize this might be a little bit confusing. I hope it's not. Basically, we're going to use the optimally shaped cone, which we know that's the one that has r equals 5.1 and h equals 7.2. We're going to use that to figure out a particular solution to this guy that we just found, okay? Given that k from the previous one is that. So we have this and this. Here's our general solution that we just had. That's x log kx minus x plus c, plus some constant. That's a general solution. We need to find a particular solution. That's what all of this is about. So, in other words, if in order to find that we need, so this thing does something like this. Something like this. This is a family of curves that looks like this. And in order to find a particular value, find a particular c, right, then what we need to do is plug in some number and get out some number, right? So if we could plug in some value here, x, and get out some value here, call it, how about d, right? Then we'll be able to put the d here, plug in the 1 or whatever it is into there, do some manipulation, and then find the c that we're looking for. Okay, so that's the idea. That's always the case with an initial value problem. Of course, it doesn't need to be initial, okay, because what happens if you plug in a 0 into c? I'd have to use L'Hopital's rule, I think, but actually, you might get, that might be fine. But the point is, that doesn't make much sense, right? So hopefully you're able to put all this together and say, well, hold up. If we find the price of one cone, right? If we know what the cost to the company is for one cone, then we plug in a C1 and we'll get, let's just see, 1 log k times 1 is 1 minus 1 plus c. If we know what the cost of one cone is, then we have k, we'll be able to plug that in, we'll be able to solve for c. So what is the cost of one cone? Well, right here we have the material cost, right? That's how many dollars, right? So a fraction of a penny, so a tenth of a penny, per square centimeter of material. And what we want to do is say, okay, well then, how much does one cone cost? Well, if we know the cost per centimeter squared, that's surface area, right? And like I said, that it's proportional to, we should assume that the cost is proportional to the amount of material that you're using here. And so for the optimally shaped cone, that surface area is this. You just plug in the optimal values into the actual surface area and find that it's this right here. Okay, so the cost of one cone, which is this many square centimeters, should just be the cost, so 0.001745 dollars per centimeter squared times the total surface area of the cone, which is 143.230 blah 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 centimeters squared. We cancel those guys out and we get $0.249937, and that is the cost of one cone. Okay, so in other words, when x equals 1 for one cone, then the cost of that one cone, the cost of production of that one cone is 0.249937. So that's what I'm going to use right here. So when I plug in a 1, I get this out. So I plugged in my 1, the x has become a 1. All I have now is log k minus 1 plus the constant. That needs to equal 0.249937. So let's get everybody over. I could get the c by himself by doing this. 0.249937 minus log k. I'm going to wait till the end to plug that k in. And then add 1 and I should get my c. So I went ahead, Wolfram Alpha, and computed log of this number right here. It gave me negative 8.472698. You take this number minus a minus, it gives you 8.7 blah 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 plus 1. Finally, the c that we're looking for, corresponding to the particular solution that we care about, is 9.722635. So the particular solution, the cost, if we use the optimally shaped cone that we found earlier, then the cost function that we're dealing with is this guy right here. That's what we want. That is the cost of x for x. You give me x cones, I plug that in with k equals to that, and that should give me the cost, the yearly cost of making x cones that year. Problem 15. Use the particular c of x that you just found, along with the r of x that you found in problem 12, to make a model of profit. P of x equals r of x minus c of x. Use this model to determine the number of cones that Holy Cow Ice Cream and Ice Cream Accessories, rights reserved, copyright limited, should produce the next fiscal year in order to maximize their profit. If they produce that number of cones, how much profit should they expect? Okay, so we're trying to maximize profit. How many cones in order to maximize profit? So imagining, okay, profit is some function, it does something like this, right? we're looking for a max value right there. That occurs where the slope of this guy is equal to 0. So we're going to use our r of x here, or c of x here, to find a p, take its derivative, set the derivative equal to 0, and find out where does that occur, for what x value. That x value will be the number of cones that maximizes the profit. Right? We want to know how many cones should we produce in order to maximize our profit. And then we want to know, if we make that number of cones, how much profit can we expect? Okay? So I'm going to take the derivative of p, set it equal to 0 to find the optimal number of cones. And whatever that number of cones is, I'm going to plug it in here and find out how much money would we make in profit if we do that. So let's do it. P of x is r of x minus c of x. Our revenue minus our cost, which we know is x minus, use parentheses will be helpful here, x natural log of kx minus x plus 9.722635. As you'll see, that won't matter. Okay, so we have an x minus an x, right? Or minus a minus x. So we have x, let me just do x minus x log kx. Minus minus is a plus x. And then minus the 9 point stuff. So that's a total of 2 x's minus x log kx minus 9.722635. That's my profit function. In order to find its max value, or where its max occurs, I'm going to take its derivative. And that gives me, okay, the derivative of 2x is just 2 minus, okay, we got to do a little product rule here. X log x, so I'm take the derivative of x, leave the second stuff alone. Add that to, leave this alone, take the derivative of the next stuff. The derivative of that stuff, the derivative of log is 1 over stuff. Then multiply by the derivative of the stuff, that stuff is kx. And so we have 1 over kx, the derivative of kx is just k. So those are gone, and I'm just left with a 1 over x, like that. Okie doke. So p prime of x is equal to 2 minus log kx minus, well, this just cancels. The x over the x is just 1, so that's a 1. Oh, this is working out really nice. 2 minus 1 is 1, so I have p prime of x is equal to 1 minus log kx. Now, I'm trying to find out where does this thing equal 0. So, it's funny, like, we did not need the particular solution to do this. So, but anyway, okay. So I want to solve this. I want to bring the log to the other side. That's going to give me 1 log kx, like that. The x is the thing I'm looking for, so I'm going to e both sides right there. E to the 1 is just e. E log makes the thing go away. And so x is equal to e over k. Now remember that k was equal to 0.000, a bunch of other stuff. 2091. So I'm going to plug this into Wolfram Alpha and see what I get. So I use Wolfram Alpha. E divided by that number gave me 12,999.913. Now you can't manufacture 0.9 of a cone, right? So we're just going to say that the number of cones that we should produce is going to be the nearest one. So I'm going to say 13,000. 13,000 cones is how many cones we should produce. Now, I know I just said that we should hold on to as many decimal places as we can until the very end, and then at the very end you round. And so you might think, well, this is what we want to use now when we when finding expected profit. This is what we should plug in to p of x,
Well, but that doesn't make any sense to do that, right? Like, if you do it, you'll get close enough and everything will be fine. But in the context of the problem, you cannot manufacture that many cones, so plugging it into there doesn't make sense. Only integer values of p make sense in this case. Unless, at the very beginning, we had that x was equal to number of cones in millions, or something like that, in which case, well, I guess, boy, that would be a lot. That would be a ton of cones. We're talking about, what, billions or trillions of cones? What, who cares? Anyway, the point is, yeah, trillions of cones, 12, 13 trillion cones. You're not going to make that many cones. But the idea then would be like, or if you have, you know, some fraction or whatever, this might actually make some sense, right? It would say make 12 mil, oh man, you see what I mean? Like, if your final answer was like 2.7 and x were in millions, then this would mean 2,700,000, right? And that would actually make sense to use that in your final calculation. But here, since x is just pure numbers of cones, let's go ahead and round it right now to 13,000, to the nearest actual cone. If you didn't do this to calculate the final thing, I'm not gonna gig you for that. That's fine. So this is what we want to do, right? I'm gonna plug this guy into here for my final answer and get. Let's see what we get. Now you actually do need the 0.9, the particular solution, to find the answer here. So we have p of x is equal to x minus x log kx minus x plus 9.72263. Like that. When I did that a minute ago, did I distribute that into everything? I don't know if I did. It doesn't matter. It didn't matter when taking the derivative, right? Minusing off the cost. I'm not sure what, if you don't understand what I'm saying, I'm not sure if I did this earlier and then added that guy. Doesn't matter when you're taking a derivative because he's a constant term. He just comes out. But at any rate, yeah, no, we did this. And then the x comes over and that gives you a 2x minus x log kx minus 9.722635. I plug in my magic value of 13,000 and that should give me a maximum here. Now, if you wanted to be sure that it's a max, not a min, we could take the second derivative and keep going from there. I'm not looking for that. It turns out to be a max because of the way I set this problem up. But like, if you didn't know, you would want to check, and you would want to graph. As soon as you had p of x right here, you would want to graph this bad boy and see what he looks like. Okay, but I'm not worried about that right now. I'm going to plug in a 13,000 equals 2 times 13,000 minus x. X is 13,000. Natural log of k was my 0.0002 stuff, which we'll get to, and then 13,000. So that's all of that now finally minus 9.722635. Plugging all of this into Wolfram Alpha, I get that the profit that we make if we manufacture 13,000 ice cream cones is 12,990.19046. But this is in, this is dollars. So we probably want to just report the actual dollar amount like this, 12,990, and then we'll say 19 cents like that, right? Because yeah, for whatever reason, we don't care about, in our purposes, we don't care about anything less than pennies, right? So finally, yes, in order to maximize profits, Holy Cow Ice Cream and Ice Cream Accessories should produce 13,000 cones next year, and if they do that, they can expect to make a profit of $12,990.19. Problem 16. Recall that the Laplace transform of a nice function, f of t, is defined as the integral from 0 to infinity of e to the minus st times f of t dt. Find the Laplace transform of f of t equals sine t. And yes, sine t is very nice. Okay? So it's just straight up compute it, right? Everywhere that you see an f of t, we're replacing it with a sine t. So that the Laplace transform of sine t, is regular old sine t, is the integral from 0 to infinity, e to the minus st sine t dt. Now, what do we do? Well, I'm not seeing anything inside of something. I'm not seeing like a sine of e to some stuff. I'm not seeing functions in functions. I'm seeing a product of functions. So I'm thinking maybe we'll try u substitution first. And there's a couple ways that this could go, really. And you could choose this to be the sine stuff or the e to the minus st stuff. Let's do sine. So that du is then cosine t, okay? Then my dv is all of the other stuff, e to the minus st. Now, the antiderivative of that, remember t is the variable. In this case, s is the constant. And so we're going to have a negative 1 over s to kill off the minus s that's going to come when I take the derivative. Let's just check. Take the derivative of this, you get e to the st. What pops out? Well, the derivative of minus st with respect to t, which is just a minus s. So the minus s pops out, kills the negative 1 over s, and we're back to where we start. So that looks good. So uv minus the integral of v du. Here we go. uv is going to be the sine t times all of this stuff. I'm going to pull the constant out front and go minus 1 over s, like that, e to the minus st, like that. So that should be u times v right there. Minus the integral of, oh, and let's not forget, we also need to evaluate these guys at their endpoints and stuff, where t goes from there to there. Well, let's just finish this up from 0 up to infinity of v du. So the v is this stuff. That's a constant. He could come out. So how about plus 1 over s is what comes out. v du is this, so we have a e to the minus st cosine t. And I didn't put my dt here, but that's what's there. Okay, so let's stop for a second and evaluate this guy. So minus 1 over s sine t e to the minus st at infinity and down at 0. So at 0, this is going to be easy to see. If you just plug in a 0 here for t, you get a 1. Plug in a 0 there, you get sine of 0 is 0. So that's going to go away. So I'll have something minus 0. The only other thing I need to do is take a limit as, let's call it n goes to infinity, of negative 1 over s sine big N e to the minus Sn. Now we have to make an assumption and assume as long as s is a positive number, then this thing will converge. So when s is positive, then negative s is negative. And taking n going to positive infinity, this thing right here will go down to 0. And so that should go to 0 in both cases. And so we could replace this whole thing right here with a big fat 0. Nice. Okay. So that gives me 1 over s, the integral from 0 to infinity of e to the minus st cosine t dt. Oh, looks like we got another product. Let's do it again. Let's do another integration by parts here. I'm going to choose cosine to be my u, cosine t. It would have worked the other way around. It's been all right. Probably, I think. Take the derivative of cosine, you get negative sine.
dt. The dv is all the other stuff, and so that's going to be e to the minus st dt is the rest of the stuff. The antiderivative of that, we just computed that. That's negative 1 over s e to the minus st, just like that. Okay, so let's do the substitution. Only now I have to be careful, 1 over s times, because that's a constant, right? And this is the only part that I'm transforming here, or I'm using integration by parts on. So uv is negative 1 over s. How about we'll do the cosine first? Cosine t e to the minus st. So that's the uv. We're going to evaluate them up at infinity down at 0 minus the integral of v du. So, okay. This, yes. So the v has a minus 1 over s, so just like last time, we'll pull it out as a positive, 1 over s like that. That's a negative. So when I put them together, it'll be, let's see, let's do the e stuff first. E to the minus st. And then negative sign, I'm going to pull out that negative and make him negative again, like that. So now we're left with that right there, sine t dt. Okay, let's evaluate this. Okay, so we have this thing right here. Oh, and this is like that right there. That's all of that. This 1 minus s has to go into everything here. So when I do this, this is the same thing as the limit as n goes to infinity of minus 1 over s cosine n e to the minus sn, which means the limit as n goes to infinity. And then I subtract off what I get when I plug in a 0 for t. So that's 1 minus s. Cosine 0 is 1. E to the 0 is also 1. So we got that. Now again, if s is positive, this right here goes to 0. Cosine keeps bouncing back and forth, but always between 1 and negative 1. And so then, since that guy's going to 0, this whole thing is going to go to 0. And so what we're left with is a negative 1 over s times 1 is still negative 1 over s. So negative is then positive. So I need to be careful here. But this entire thing worked out to be negative, so positive 1 over s. Okay. Now, minus 1 over s, integral from 0 to infinity, e to the minus st sine t dt. Uh-oh. Well, hold on. Let's just go ahead and do this. I'm going to bring him through. We have 1 over s squared, because I'm multiplying through here and then into here, minus 1 over s squared, the integral from 0 to infinity, e to the minus st sine t dt. Uh-oh. Do we keep going back? Do we go back to where we started? And do it again, and again, and again, and you can see it'll never end if you do that. You should remember there's a nifty little trick when this type of thing happens, okay? So let me rewrite this. Remember, this is how we got here. That's all the work we got there. But at the very beginning, all of this has always, the whole time, been equal to this. So I'm just going to replace this right here with my original bit. And we have from 0 to infinity, e to the minus st sine t dt, which is the thing we're looking for. And now it shows up on two sides of the equation. So if you remember the little trick, when you're doing integrals and something crazy like this happens, what I like to do is I'm going to give the integral itself a name. I'm going to say that this whole thing itself is I. That's my integral. And so since it's the same thing over here, I'm going to say that's also I. That's my integral. So in other words, I'm saying that I is the integral itself that I'm trying to compute right here. E to the minus st sine t dt. That's what I means. I'm just going to make it a little bit easier on my i's here. My EYES. And so now replacing those to make this a little bit easier. Now I have this.
Now I have an equation involving one unknown, and if I just rearrange it, I could get that one unknown by itself, which is the thing that I want. So I'm going to do that. I'm going to get all of my i's on one side. I plus 1 over s squared I is equal to 1 over s squared. Factor out my I. 1 plus 1 over s squared. So 1 over s squared, like that. Now I'm just going to divide. And I get that I is equal to 1 over s squared times 1 plus 1 over s squared. Like that. Is that right? Let's see. So what we just found, that was the integral, but the integral was the thing that we're trying to find. So we just found, let me rewrite this here, that this thing, I, is equal to 1 over s squared times 1 plus 1 over s squared. Now, that's not what my table said it should be. I think my table, my Laplace transform table, when we had our f and L of f, I'm pretty sure it said something like this, sine of at. If you take the Laplace transform of it, it was like a over like a squared plus s squared or something like that. I'm not sure where the a showed up or if it was squared in the top or not. I think it was. Who cares? Because watch, this actually is the right thing. Because watch, I'm just going to multiply this through 1 over, multiplying him through, we get s squared. Multiplying him through, I get s squared over s squared is just 1. And yeah, indeed, I think that's the same thing. And so there you go, there's your answer. The Laplace transform of sine t is equal to 1 plus, or I'm sorry, is equal to 1 over s squared plus 1.